Yeah. So hi everyone. So welcome to the Bangalore Theory seminar series. So today we have with us Ayush Sekhari, who also joined us last week for his talk on unlearning, and today promises to be yet another important problem in the area of RL. So we are going to speak about learning from offline data. So, to tell you a little bit about Ayush, Ayush is a postdoc researcher working at MIT with Professor Sasha. He completed his PhD from the CS department at Cornell, where he was advised by Professor Karthik Sridharan and Professor Robert Kleinberg. His research interests span stochastic optimization, RL, and machine learning. So, before his PhD, he also spent a year as part of the inaugural Brain residency program at Google Brain. And prior to that, he had obtained the President's Gold Medal at the CIS department at IIT Kanpur. He's always present in most of the major ML conferences, and he's prior to this been a winner of the Best Student Paper Award at Colt 2019. So without further ado, I'll hand it to Ayush for his talk.
Great, thanks Rahul for the kind introduction. So is the recording on?
I see it as on.
Okay, cool.
You
I
go
don't
ahead.
see the Teams page because I'm sharing the screen. Okay, so I'll start now. So this is
Yeah.
joint work with uh should I start? Cool. So
Yes,
this is
please
joint
go ahead.
work. Mhm. This is joint work with Yifei Zhao at UC Berkeley, Yuda Song at CMU, and Wen Sun at Cornell. I'll provide a brief overview of the talk. I'll first provide some introduction about why we care about this setting, then go into the actual setting and technical details of the MDP that we will be working in. Finally, provide our algorithm and then some theoretical analysis and experiments. Cool. Let us start with some introduction. So over the past few years, we have seen many success stories of empirical reinforcement learning. And these success stories have demonstrated that using function approximation along with reinforcement learning can work well in solving many challenging problems. However, if you go into any of these stories, you will see that there's a lot of moving parts. It's a big experimental project. There are so many components that need to be optimized, so much of intuition and so on. And it's not clear whether we do have like optimal or good algorithms that will just work out of the box on the new problem. So the goal of my work from the theory side is to try to develop provably efficient algorithms that could work in MDPs with large state and action spaces. And typically, in the direction of coming up with provably efficient algorithms for large state space or action space MDPs, there are two high level directions. The first direction is that of model based RL, where as a learner, we try to model the dynamics of the environment and we try to learn it and then use the learned dynamic to make the decisions. And the other direction is that of model free RL, where we don't really try to learn the exact dynamics and model the dynamics, but we try to model the value functions and we try to learn the value functions, which can help us in making decisions. And the goal of this talk will be in model-free RL. In model-free RL, there are further approaches that people have been taking in order to come up with tractable algorithms. And the vanilla approach in this direction is that of online reinforcement learning. This is a very simple setting where we assume that the reinforcement learning algorithm collects all the data that it needs to learn by interacting with the environment. So,
Quick question, Ayush.
mhm,
Sorry, just to clarify, when you say model-based RL,
mhm,
what you would try to learn is first the transition probabilities,
yes,
and then possibly go on to learn the value functions. Whereas in model-free RL, you're directly learning the value functions associated with states. Is that understanding right?
exactly. So either you try to learn the transition probability, or if there's like some underlying structure like LQR, you try to learn the exact dynamics and so on. And in model free, you
Right.
don't really try to learn the dynamics, but you directly learn the value functions.
And implicitly is the transition probabilities getting learned, or uh,
Not really. So you directly try to learn the value functions, and that's by choice because it seems like learning the model requires more parameters. It's going to be a more expensive talk. So if we can solve the problem by directly learning value functions, we should do that.
Mhm. Okay, thank you.
Mhm. Okay, so the first approach is that of online RL, where the algorithm collects all the data that it needs by interacting with the environment. However, there's a key challenge in this approach. The challenge is that because the online algorithm is collecting all the data it needs, it has to balance exploration versus exploitation. In particular, it has to balance the objective of maximizing what it wants to do, like collecting rewards, along with exploring in the environment to get more information about the environment, which will help it in getting better rewards in the future. And it has been observed that exploration is actually challenging in many environments in the real world. And on the theory side, there have been a lot of work in trying to develop algorithms for online RL, which works with function approximation. And by now, we do have a good sense of what is the landscape of statistical efficiency. And in some cases, we even have optimal statistical algorithms. And we have tried to develop a lot of structural conditions and relations between these structural conditions that allow us to understand when is exploration or online RL tractable. So there's this slide that I borrowed from Akshay that tries to incorporate a lot of these structural conditions in relation to each other. And the so like the most general one in this is that of decision estimation coefficient, which also has some lower bounds and the statistical optimality. And then there are like simpler models like low rank MDP, linear MDP, and so on, where we have like computationally tractable algorithms, etc.
So,
Mhm,
can I take a second to understand this figure? So I understand the parts which are inside,
mhm,
perhaps a little bit more than the outside ones.
mhm.
So are you saying that each of these is like a computation, like similar to computational complexity class, increasing in the sample complexity space, or to
Yeah, so
learn?
each of them is a structural condition, and you
Mhm.
can prove things like the structural condition that the MDP has a low Bellman rank, which I will not tell you what it is. It captures all the MDPs that have low rank, and it captures all the MDPs that are linear MDPs, and so on. So these are all just like structural conditions that try to understand when sample a statistically efficient online RL is possible. And if you look at the corresponding sample complexity, a quantity like rank will appear in the bound.
Mm. It's interesting because I thought rank would appear, and rank seems to be a very linear way of proposing things.
Right.
But the fact that eluded dimension also appears means that there could there could be something else going on, but you could still break it down into some equivalent function complexity.
Exactly, exactly. So this has been a very active area of research recently in trying to come up with the right structural conditions that allow for exploration and online reinforcement learning. However, a key problem with this direction is that most of the general purpose structural conditions are the corresponding algorithms are not computationally efficient. And in some cases, we even know like hardness results that you cannot implement the proposed algorithms for those settings in a computationally efficient manner. So this effort has been mostly statistical, and there's a computational statistical gap in the sense we do understand what structures allow for exploration, but it's not clear if we can actually come up with practical algorithms that can be used in the real world.
Just to clarify, you mean they might be sample complexity wise efficient, but once you get the samples, it's computationally inefficient to compute, let's say, the value function.
Exactly.
Okay.
And there are actually like examples, for example, this problem of sorry, not linear Bellman complete. It's called linear Q star.
Mm.
Uh, you can like Google this keyword later. The exact setting is not important, but you have a statistical computational gap over there.
And when you say inefficient, it means not polynomial in, let's say, the
Exactly,
dimension.
exactly, exactly. Not polynomial.
Okay, thanks.
So not polynomial in the respective problem parameters, like not polynomial in rank and like 1 by epsilon and so on.
Mhm.
Right. Okay. On the other hand, there's this effort in online reinforcement learning of developing on-policy methods. So these are approaches like policy gradient, natural policy gradient, PPO, TRPO, etc. And these algorithms are interesting because by design they are constructed such that the algorithm optimizes the cost function of interest, and there's some gradient that increases the objective, and so on. And these algorithms are typically less statistically efficient than off-policy methods that are described in the previous slide, but they're implementable in practice. In fact, if you look at a lot of empirical RL literature, they will generally be using some version of PPO or TRPO and so on. However, on the theory side, these algorithms are not super well understood. We do have some guarantees, but they only occur under very strong assumptions. In some sense, you need to require some coverage over the state space via some initial state distribution and so on.
So I
And
didn't follow.
mhm.
I'm sorry, but I didn't follow one thing. Why are they less efficient? I would have thought they're more efficient because you are getting samples from the distribution you want to emulate.
No, but
Whereas your
still they
policy,
are somehow less efficient. We don't know of like even in theory they're less efficient, and in practice they're less efficient in the problems where we can implement them.
okay. Yeah, but these are the more popular ones, I suppose, than your policy.
Yeah, yeah, because by design they are very simple to implement and like you can actually run them and so on.
Mm.
So even though they are not optimal in terms of like how to balance exploration and exploitation, uh,
Mm.
they're so easy to implement that like you can actually run them for any problem.
Mm.
Okay, so the takeaway from these two uh, different worlds of online RL is that in a sense these algorithms are not really efficient in practice, either computationally in the first case or statistically in the second case. Okay, so then
But
there's another approach. Sorry, go on.
one might argue that computational efficiency does not matter because compute comes for cheap, whereas
Right.
samples are expensive. So, is that really a major concern, like computational efficiency?
Yeah, yeah, yeah. So the kind of algorithms, the kind of objectives you need to solve for the previous slide version are
Hmm?
actually like extremely hard. So they are like exponential time in like rank or so on.
I see. Okay,
So I think like given the current standards of computation, it's still difficult to implement them.
I see. At least at scale. Okay.
Yeah. And in fact, like there are some separations where I told you about this linear Q star problem.
Hmm.
Over there, you can show that if the exponential time hypothesis holds, you do need like exponential in rank running time in order to solve the problem, even if it is statistically efficient.
Can I understand this figure a little more? Because maybe I did not understand it the first time we went through it. Is this uh, is this a, property of the instance, or is this the property of the model, or is it a property of the data, or
Yeah.
like what's happening
Uh,
here is
mhm.
there's data coming at us and we don't know where it lies. So we model it, and depending on how we model it, this is the complexity we face.
So this is the complexity of the model.
Mhm.
And
Okay.
you typically assume that the problem that you're solving is captured by that model family,
Mhm.
right?
Right, right. Okay, thanks. Thanks.
Mhm. Okay, so the other approach that is a common direction in RL community is that of offline reinforcement learning, where the idea is like don't worry about online interactions where we have to balance exploration, exploitation, and so on. Just rely on data sets that we have already collected. There are huge internet-sized data sets that we have collected of interactions and so on. And can we use these pre-collected data sets for learning? In a sense, like can we train a policy or some value functions for learning uh, by just using the big data sets constructed from past interactions and not doing any new interactions with the environment. And while this problem setting is interesting, making offline reinforcement learning work reliably is very hard. And there are two main issues where this hardness comes from. The first issue is that of distribution shift. In a sense, when you collected an offline data set, you have some distribution over the state action pairs, and that constrains the kind of things that you can optimize over. So this requires us to restrict algorithms that respect the distribution of the offline data in order to find the return policy. And this has led to techniques like pessimism and so on, which are also not computationally efficient when done with general function classes. On the other
So,
hand, when you try to run these algorithms in practice, if you look at the learning curves, they're crazy. Like they look very jittery and so on. And it's not even clear like how to tune the hyperparameters of in offline RL, like and when do we stop training and so on and so forth. So there are a lot of like theoretical issues concerning distribution shift and practical issues concerning like implementability of these algorithms. And if you look at like the landscape of when do we even have statistical tractability in offline RL, it is even worse than what we have for online RL. In fact, like most of these cases that we discussed in online RL are not or we don't even know yet whether they are statistically tractable or not.
so
And
even
mhm,
yeah, this is surprising. So even in the linear Bellman case, it's not known, is it?
yes,
Uh, so I would have thought like
actually,
maybe it's
we have lower bounds. Like there are some new works that show statistical lower bounds now in linear Bellman complete.
right, but no upper bounds.
Oh,
Okay,
lower bound in the sense like it's intractable, statistically intractable.
I see.
Mhm.
So yeah, that's interesting. But my question was, given offline data and under certain assumptions on the offline data, can you not do some kind of importance sampling to account for the distributional shift from the online setting? So if you were able to, if you had D and you knew your on policy was D prime, could you not importance sample as per D prime?
Yeah, so you pay for the price of distribution shift over there, right?
Mhm.
So that naturally restricts you to only look at distributions that are close in the sense of this L infinity norm of the ratio
Mhm.
of the two densities to the distribution that was provided to you. And that kind of restricts the class of policies that you can return, right? So there's always a distribution shift problem. You're like restricted to be close to whatever distribution that was provided to you.
Right. And I see why you say L infinity norm because you're constrained by the worst case.
Yeah, that's like just to like align with your example. Because if you do
Mhm.
importance sampling, you will need to pay for this distribution shift in this norm.
I see. Yes. Yeah. Thanks.
Mhm. Cool. So the landscape so far is that there are two different directions, one of online RL and one of offline RL. And we have seen that these things, there's a gap between like computation versus like what we know from the statistical side. In particular, the methods are not computationally efficient. So the key idea of this work is to use both offline and online data. So combine the best of both. And this is what we call as hybrid RL setting. So this is a paradigm where an agent is trying to learn a policy, given access to some offline data, While in addition to the offline data, it also has access to online interactions with the real world. So it can collect fresh data corresponding to whatever policy it wants, in addition to this big offline data set that is already provided to it. So this is what we term hybrid RL. And hybrid RL is not super new setting. It has been used in various forms in prior both theoretical and applied works. On the applied side, even things like AlphaGo actually use some version of both online and offline data. And robotics, people generally use some expert trajectories to start with, and then they collect more trajectories and so on. And even ChatGPT, if you look at like how it is trained, there's a pre-training phase which is done on offline data, and then there's a fine-tuning phase which is done on online data, and so on. And on the theory side, people have been exploring this paradigm of combining both offline and online data in various settings, including these past works of Kakadi and Langford and Drew Bagnall et al., which explored this hybrid RL in a reset model where you do have online interactions, but then you can like go anywhere and then take a query and see what happens. And in this model-based method, including some work from Ross and Bagnall and so on.
So
Mhm.
maybe I have a quick question regarding. I'm not sure how faithful the image on the right is. So if I understand you right, you will, let's say, on policy take some action, receive some reward information, and then train to convergence with this new information.
Exactly, exactly. So this will become more clear when I provide you the algorithm. But this picture just wants to convey the paradigm that you're using both online and offline interactions.
Okay. Yeah.
A quick question over here. So, is there a particular ratio in which you mix this online and offline data? Because the examples you gave, they usually use more online data compared to the offline one. So, is it
Wonderful.
the same way or different?
So this will become more clear as I provide the algorithm and guarantees and so on. So let's
Okay.
wait on this question for a bit and we can come back. Okay, so the most relevant work to this particular paper is some of my own prior work. So we had this paper last year, which we called hybrid RL using both online and offline data can make RL efficient. And the key contribution in this paper was to provide an algorithm that we called HiQ that works with general function approximation. I'll clarify what these terms mean as I go into the formal setting. But for now, just for those who know this word, so it works with general function approximation. But more importantly, it only relies on square loss regression over this function class. So it's like a computationally efficient algorithm provided you can do square loss over the given function class. And what this guarantees is it can produce a sequence of policies pi1 to pi t, such that if I look at the average cumulative suboptimality of the sequence generated by my algorithm with respect to any comparator policy of choice, it's upper bounded by this expression where there's a term C pi e that corresponds to the coverage or this distribution shift for policy pi e in comparison to the offline data. Some structural property of the underlying MDP, for example, this bilinear rank, etc., that governs the statistical complexity of the problem, and some log f and log 1 by delta terms. So at a high level, this work provided a computationally efficient algorithm for a general class of problems by combining both online and offline data. However, there are a few limitations of this kind of result. The first limitation is that this algorithm can only compare with policies that are actually covered by the offline data. So we have not really resolved the distribution shift issue yet. This algorithm also requires this notion of Bellman completeness. I'll clarify later what this means, but this is an extremely challenging assumption to hold in practice. And finally, when this assumption does not hold, by the design of this algorithm, it could actually be unstable in practice and it may not converge and so on. On the other hand, the bound over here also depends on this bilinear rank D. And it's not clear whether these kinds of structural assumptions are actually necessary in hybrid RL. So the goal of this work is to actually circumvent these issues from prior hybrid RL world and provide an algorithm that can actually
Quick
combine
question.
the best of both online and so just let me finish this. Best of both online and offline data. So in particular, we want to provide an algorithm that benefits from access to offline data when the offline data is nice and additional assumptions hold and so on. However, when the offline data is not useful, it at least retains guarantees from some online RL. And our goal is to do this computationally efficiently. Question?
Yeah, sorry for the interruption. I maybe want to have some clarification on the previous slide. So this function class that you mentioned,
Yeah.
it often is not a bounded function class. So what is the log dependence on the cardinality of f mean? Is it
Yeah.
of
So
rank of?
for the sake of this talk, you can assume it's bounded, but otherwise, like you can paste some sort of covering numbers and things like that over here.
Mhm.
So our
And
focus is not on like this discretization of the function class, but more on the sense of like what we do with it. Mhm.
right, right. I want to understand the linear term slightly more. So what would CPI indicate here? Or would you be going into detail
I will
further
be going
later?
into all of these details in a bit.
Okay, thank you.
Mhm. Cool. So okay, so I've shown you like what the landscape looks like. There's offline RL, online RL, and we want to do hybrid RL. And there is a prior work in this direction. However, it has some limitations, and we want to overcome those limitations and come up with a really like best of both worlds kind of guarantee. Now let me actually go into the technical details and exact setting and so on that we'll consider for the rest of the talk. So formally, we consider the setting of discounted MDPs. So a discounted MDPs has 6 components associated with it. There's a state space S, there's an action space A, there's a something happened with the arrows, but uh, ignore that. So there's a transition dynamics T, there's a reward function R, there's an initial distribution mu naught from which an episode is sampled from, and then there's a discount factor gamma that discounts the return rewards as we collect. And we assume that learner has online access to this MDP in the sense at will the learner can come up with a policy pi, sample the initial distribution S naught from mu naught, and collect a trajectory by taking actions according to pi, starting from the state S naught from mu naught. Associated with a policy pi, there is this notion of value function. So there's a state-dependent value function v pi. Okay, so first of all, there's a value function associated with the policy. So v pi just denotes the cumulative discounted reward that we will get in the MDP if we execute it using the policy pi, starting from some S naught A naught drawn from U naught. Then there is this notion of state action value function Q pi that is associated with every policy pi, such that for any state action SA, the value of Q pi SA is just the cumulative discounted reward that we will get if we start from SA and continue forward using actions taken according to pi. And then there's this notion of occupancy measure of a policy pi, which is just the cumulative distribution over the state space, cumulative discounted distribution over the state space that we observe when we start from some state SA, start from the initial distribution mu naught and run the policy pi. Okay, so these were the MDP preliminaries. Then we
Question.
also, sorry, go on.
So just to clarify, the expectation is over the initial states, sample as per mu naught as well as over the actions given by the policy. Is that correct?
Yeah, as well as the dynamics of the stochastic dynamics of the MDP.
Okay. Yeah.
Right. So typically, we do not assume that we know the dynamics or the reward function of the underlying MDP. So these are the things that need to be learned.
And in your case, is the reward also stochastic? It could be like no
It could,
assumptions on reward. Or...
yeah.
Okay, thank you.
Mm-hmm.
Can you explain occupancy measure in a bit detail?
Yeah. So occupancy measure is more like, okay, so you start from some initial distribution over the states. Then you take the action. Okay, so you start from S naught, A naught. So you then go to S1. Then you take the action according to pi, you go to S2. Then you take another action according to pi, you go to S3 and so on. So at every time step, there is a marginal distribution of over the state space cross action space. And the occupancy measure is just a cumulative sum, like discounted sum of these marginal distributions. And you can
Okay,
think of
and
this
while
as follows. If you stop the trajectory with a probability of, I think with the rejection probability of 1 minus gamma, sorry, 1 over 1 minus gamma, then what's the marginal distribution over the state space that you will observe? So that's exactly given by this occupancy measure.
okay, got it. Yeah.
So this is a very important quantity when dealing with the behaviors of policies on the underlying MTP, as will become clear from next definitions. Okay, then we assume that we have access to an offline data distribution nu, which is a distribution over the state space cross action space. And we assume that the learner can collect data from this offline distribution, where the learner at any time can request an offline data tuple SARS prime using this offline distribution where SA is sampled from nu. The reward is whatever is sampled from the underlying MDP when you take action A on the state S. And S prime is one step transition in the underlying MDP starting from S and on taking the action A. And an underlying assumption is that this offline data is sensible in the sense like it covers some good quality policies, which I'll clarify in a bit what I mean by that. Okay, then we consider the function approximation setting. Here, learner has access to a value function class scriptf that contains functions that maps states and actions to some real values. Furthermore, we define this notion of a Bellman operator associated with a policy pi, the script pi, which is defined such that if I give you a function f in this class scriptf, the function script pi of f is defined as follows, which captures a one-step backup in the MDP of the function f corresponding to actions that are taken by pi. So in particular, if you look at t pi of f at SA, this is essentially the sum of reward of SA plus gamma times you take a action corresponding to pi and a transition corresponding to so you first go to a next state corresponding to a transition from SA, and then you take an action according to pi on this new state S prime, and you evaluate this function on the tuple f of S prime A prime. So while it's not super essential for most of the technical details, there's a crucial definition that depends on this Bellman operator, and that's why we need to just keep this around for some time.
So typically, this Bellman operator is used on the discounted rewards, but you're defining it more generally for any function f. So I'm kind of guessing it's like the push forward of the function for one step.
Exactly. right? So you can define this operator associated with any policy pi and apply this on any function f that you like.
Is there a set of properties that this operator has to follow?
Yeah, we'll come to it. Okay, but so these properties and so on are more in the place of like assumptions that we require for an algorithm to work. But let me like go into the algorithm first, and then we can go over the theoretical analysis and the kind of properties we need. So our key contribution in this work is to provide this algorithm called hybrid actor-critic, which is a computationally efficient on-policy algorithm that uses both online and offline data. The algorithm is actually very simple. It has two components. The first component is what is called hybrid actor-critic. It performs as follows. So it initializes some policy which could be uniform over the action space. And then it does many iterations, where in each iteration, you first estimate a function ft that corresponds to the value function of the current policy pi t. So this function ft corresponds to q of pi t, which is the state action value function associated with the policy pi t. And once you compute the function ft, you just update the current policy pi t in this manner, where you reweight the actions proportional to the value function, like exponential of the value function. And eventually you just return a uniform distribution over the policies that you have seen so far. So the key idea is that this value function estimate is done using a sub protocol called hybrid fitted policy evaluation that uses both online and offline data in order to compute this estimate of the value function corresponding to the policy by t. Okay, any question at this first component?
I would like to understand if you have time on on line 2.2 more. So you do get information only for one AS pair, but you are computing for you are updating the policy values for all the pairs. I'm not wrong.
No,
So
no.
they don't really
Basically,
change, right?
so there's a policy that is changing,
Mm-hmm.
and corresponding to the policy, this hybrid fitted policy evaluation collects a lot of online and offline data.
Mm-hmm.
And after collecting a lot of online and offline data, it generates a value function for this policy, which you
Right,
just
right, right.
apply globally to update the policy everywhere.
I see. And if I can understand right, at this point, it's still pi. Yeah, okay. Okay. And nowhere is it very clear to me that this is going to get you to pi star or anything, but that might come in the analysis.
Exactly, exactly. So it has some like greedy flavor to it if you think about it, right? You estimate the value functions and then you favor the actions that have higher value functions.
Hmm.
In the second step after exponential, what is this eta?
Oh, there's just some learning rate that you choose.
Okay.
Yeah, yeah.
So
Good.
it's a
So,
diminishing learning rate or is it a constant learning rate?
No, no, the learning rate decays. It's something like 1 by root t uh, if you run for t
Okay.
iterations.
Okay.
There's like a typical, it follows from a typical analysis for some sort of like exponential weight style algorithm.
so for example, if your eta were to be, I'm guessing high, then you would overweight the FT values, which are
Right,
high.
right.
But I'm guessing that's not what you want to do at the start because you're not that sure.
Exactly. That's not what you want to do because your first policy could actually be like a suboptimal policy and its
Mm-hmm.
value functions may not correspond to. So you need to like correct this slowly, basically.
Right, right. Makes sense.
Okay, now let me go into hybrid fitted policy evaluation. So this is the protocol that we use to compute the value function. So given the policy pi whose value function you want to compute, this protocol is as follows. This is where all the action happens. So it initializes a value function and then performs k loops, where in each loop, the algorithm first collects a few on-policy online samples. So we first collect samples SA and a Monte Carlo rollout of the value function by running this policy pi on the MDP. Then it collects some offline samples of the form SAR S prime by sampling using this distribution nu. And finally, it fits a value function that minimizes a loss on the offline data and a loss on the online data. And the key idea is that if you look carefully, this loss is essentially a square loss problem. And finally returns the average value function that you have seen so far. Okay, so taken together, there's this hybrid actor-critic that performs an update on the policy by using estimates of the value function. And then there's a hybrid fitted policy evaluation that uses both online and offline data to come up with an estimate of the value function that is used to update the policy. And the important place where the main computational bottleneck is in algorithm hybrid policy evaluation. But as I observed, this thing is actually solving a square loss regression problem. So if you can do square loss over this function class, you're actually good to go.
Some sort of gradient descent would work, I guess.
Yeah, like whatever way you like to implement square loss regression. Typically gradient descent, yeah.
So HAC line 2. So you say return pi hat is uniform over pi 1 to pi t. But I thought, like, if you were improving, why not weight yourself heavily to pi t rather than why do you sample uniformly? So that's my question.
So this is like a typical thing when it comes to analysis of online algorithms. What you like, you have these telescoping terms that come up, and you need to aggregate in order to cancel them, and so on. So but in real world, we actually implemented it without this uniform averaging, and it kind of works. So
you might just return pi t or something. You might just return pi t or something.
Yeah, exactly.
Okay.
Okay, so I have 10 more minutes left. So let me go to the part where I show the guarantee, but not go into the proof, but that will already establish the assumptions that I need, and then go into experiments. Okay. So now we want to analyze how this algorithm performs or when it performs. And there are a bunch of assumptions and definitions that we need to make to provide this analysis. This first assumption is what is known as realizability. And this is very common when you are dealing with value function approximation in reinforcement learning. So at a high level, this assumption just says that the value function class scriptf that was provided to the learner is rich enough to the value functions corresponding to different policies. And this is kind of natural in the sense, if you look at the algorithm, it's using the function class to represent value function and so on. So we can just impose this as assumption that it can exactly represent the value function for different policies. Finally, there's this notion of inherent Bellman error, which is associated with this operator that we discussed of policy-specific Bellman operator. And it's defined as follows. We say that the class scriptf has pointwise inherent Bellman error denoted by epsilon BE. If for all functions in this class and all policies, there exists some other function such that that other function corresponds to applying the Bellman operator associated with policy pi on the function f. And the gap in this estimation, gap in this expressivity is what we denote by epsilon BE. And the idea is when epsilon BE is 0, then for any function f, we can express its Bellman, its operator, the corresponding function obtained by applying Bellman operator for any policy in the same function class. In particular, we can also express its Bellman backup, which is the Bellman operator associated with the optimal policy. And this This definition is known as Bellman complete. Okay, so from this slide, you can imagine that this is actually a kind of strong assumption because you're saying that if I take any function in my value function class, apply this operator, I can again represent the obtained function in the same function class. And it's not clear whether it will always hold in practice or not. So the key idea is we kind of want results which can hold in the absence of presence of this particular requirement that this Bellman error is small. And we'll provide one such result in a few slides.
So, quick question. Sorry for interruption, but is it such a strong assumption? For example, if f is large enough, for example, it's continuous, this property should be satisfied, no? Like,
Not really, like it's actually not monotonic in the size of f because if you make f larger, you're also requiring these backups to be in the same class for more and more functions.
mhm.
Right? So this is actually like a very non-trivial assumption.
I see.
You
Okay,
can
we
have
can
things
just
like this in like linear settings. So if you assume that all policies have linear value functions, then
then
you can
it's
say
carrying.
when I back them up, they will again be linear functions and so on. So it's closed in the same class, and this is what is called a linear Bellman complete problem. But it
Or
seems
for
like
that matter, polynomial, any
hmm?
polynomial, or for
Yeah,
that matter, any polynomial
exactly,
class.
exactly. Like polynomial linear in some high dimensional featureization.
Yes, yes.
Yeah, yeah. So that's like one setting where we know we can hope for some kind of disclosures, but in general, it's not clear whether this holds or not.
Got it. Okay.
Just a quick question. How do you come up with this assumption? Means what was the intuition behind it?
Yeah, yeah. So this assumption is actually very natural when it comes to analysis of this policy fitting based algorithms. So if you look at the way this oracle is designed, it's optimizing an objective, the first objective over here. Its expected value like is very close to this policy specific Bellman operator. So in the analysis of the square loss, you kind of like rely on this kind of completeness so that you can argue that Bayes optimal is in the class and so on and so forth. So this kind of assumption is very natural in a huge amount of RL literature that relies on value function, like fitted iteration for computing value functions.
Okay, got it. Yeah.
Yeah. Okay. Then we have more assumptions on the comparator policy pi e that we want to compare with. And the first assumption is that of NPG coverage. So this assumption is again common in this policy gradient literature. This assumption is defined as follows. It just says that the policy that we want to compete with, the occupancy measure of this policy, has a bounded ratio with respect to any other comparator policy. And while this might look a bit weird, like there are examples where this holds. For example, if the reset distribution mu naught from which we start has good coverage over the comparator policy pi e that we want to compare with, then this quantity C of NPG pi e is bounded in terms of this coverage. And finally, we have some requirements on the offline data distribution. So regarding the offline data distribution, we define this transfer coefficient, which we call C of pi e. It has a kind of complex expression, but this is the tightest you kind of need for our job. But this is a ratio of the signed Bellman error under the comparator policy pi e versus that of the offline data distribution mu. And this notion of transfer coefficient actually captures various prior definitions of offline coverage. So there are these notions of L infinity coverage in tabular MDP, and in linear MDP, there is a notion of this coverage along different features and so on. Finally, the offline data is collected using some policy. So you roll out some policy. It is not hard to show that this quantity C of pi is actually smaller than C of NPG. And what we'll show is that our bounds will actually depend on these quantities that we have introduced so far. In particular, our improved bound will depend on this Bellman error transfer coefficient. Okay, so let me show the performance guarantee of hybrid actor-critic. This is the main theorem of the paper. So this is the best of both worlds kind of performance guarantee. It says, suppose hybrid actor-critic is run for t iterations with an appropriate choice of size of number of iterations versus the size of online and offline datasets. Then first of all, for any comparator policy pi e, the cumulative suboptimality of the sequence of policies that I would generate is upper bounded by some 1 over 1 minus gamma square term that denotes an effective horizon times log a plus c of npg pi e times t. Okay, so the attention here should be this term c of npg pi e. However, we also show that if your offline data and offline data assumptions hold, that you do have approximate Bellman completeness, and the Bellman error transfer coefficient is smaller than NPG, which happens when the offline data was collected using some reasonable policy. Then you can improve this dependence on NPG, say C of NPG by C of off pi e. So in particular, we recover a typical guarantee that you expect for online RL, for actor-critic algorithms in online RL. But we provide an improvement over this at the same time when the offline data satisfies good assumptions. Furthermore, these guarantees is obtained by using this submodule HPE, hybrid fitted policy evaluation, which relies on square loss regression and is thus computationally efficient. So the takeaway is that hybrid actor-critic is a simple on-policy hybrid algorithm that combines the best of both online and offline data. In particular, it enjoys polynomial sample complexity and is computationally efficient when we are given a square loss regression over this class. Okay, so this was the theorem. I'll skip the analysis for the sake of time. The analysis is not too complex, like it's a couple of pages. But I'll go over the experiments to convince you that this algorithm actually also works in practice. So we did run some experiments with this hybrid approach, and we tried this in this continuous com block environment. So this is an environment where you are given some h-step MDP, where each MDP has 3 states, and each state has 10 actions. And if you take the correct action, you go on the right path. Otherwise, you deviate and go towards the sink shown in orange. So this is an extremely sparse reward signal MDP because you need to know the right action to stay on the right path. Otherwise, you deviate. And this is a very challenging exploration problem. And we tried our algorithm over here where we collected 50,000 offline data set using some previously computed optimal policy along with some noise, and compared our algorithm with a state-of-the-art hybrid RL algorithm and a state-of-the-art fully online algorithm. And what we observed is that our algorithm can actually solve the problem in regimes where these previous approaches do not work. In particular, our approach can solve horizon 50 problems, but prior approaches were stuck on horizon 15. Then we also tried this algorithm on an extension of this previous example where instead of observing just noisy observations of the state, you actually get an image from CFAR 100 corresponding to the latent state. So the idea is we associated a class from CFAR 100 to each latent state, such that when you go to the latent state, instead of observing the underlying state, you only get a uniformly random image drawn from the corresponding class of CFAR 100. So this is a much more challenging problem because we're actually learning from image observations rather than latent state or noisy latent state observations. And again, it carries all the hardness of the previous example, like sparse reward signal, hard to explore MDP, and so on. But more typically, this is a case where Bellman completeness does not hold. So the success of an algorithm shows that we can actually work in cases where Bellman completeness may not hold. In the sense, we do have these guarantees from online, and it performs better than the prior works in this direction.
A quick question, if you can take that.
Sorry, I
Maybe
was
we
very
can go
fast
on
on
for,
this. Yeah.
yeah. Maybe we can go on for 5 more minutes if that's okay with everyone else. But my question was, I didn't understand what are the actions and states in this image-based.
Yeah. So let us go back to the simpler version first. So this is a com block environment. It's actually like a typical test bed that is used in for understanding like success of RL algorithms for exploration. So the idea is you have H many layers. Each layer has 3 states except for the first layer. Okay, and each state has 10 actions that you can take. Now the idea is from the first 2 layers, if you take the correct action, you go to the shaded one in the next state, and so on and so forth. But if you take any of the other 9 wrong actions, you go to this orange state, and then you're stuck there because there's no arrow that goes back from the orange state to this green states. And the only time you get a reward is when you complete this H-step MDP and go to the last layer and the last green state. Otherwise, you don't get any reward. Right? So in order
So
to
the
obtain the
reward is
reward,
sparse.
you need to take the correct action for all of these time steps. Otherwise, you're doomed.
So the reverse is extremely sparse because you need to take 10 actions in a row, correct?
Exactly. So if you look at it's like a needle in a haystack with the size of a haystack to be like 10 to the power of h.
Yes.
Right.
Agreed.
Okay.
So on the image
Furthermore,
side, what?
Mhm.
Yeah.
Go on.
Sorry, go ahead. Yeah, on the image side, what does this look like?
Yeah. Okay. So right now, like this is the version 1 where you can actually operate in this MDP and you can see which state you are in and so on, like you can see am I in a green state or a orange state and so on. So one version to make it a bit more complex is to actually, instead of returning the states, like a one-hot encoding of the state, you multiply it with a random Hadamard matrix and return a row of the random Hadamard matrix. Sorry, not a random, like you multiply it with a permutation of Hadamard matrix and you return a row of the like
Of the
row
permuted
corresponding
matrix.
to that one hot vector.
Would the Hadamard matrix have to be known beforehand to the algorithm, or?
No, exactly. So there's a unique row associated with every state. So it's fully decodable in the sense like you are now operating in this observations corresponding to rows of the Hadamard matrix, but you don't know which one is assigned to which one.
Right. Okay.
Right? Okay, so this is the first task, and this is a 101 test bed that you should perform when proposing a new exploration algorithm. And this version, which is image-based continuous com block, is our extension of this method. So what we do is, instead of returning this random row from Hadamard matrix, we associate one class of CFAR 100 corresponding to every latent state. So as you can see, our maximum horizon we evaluate is 30. So there are like 90 latent states. There are 100 classes. We associate one class to every latent state. Now, when you transition to a latent state, instead of observing the one hot vector of that latent state, you uniformly randomly draw a image from the corresponding class associated with this latent state and return that. So for example, if this is a dog class, every time you come to this, you get a new dog image sampled from the set of dog images in CFAR 100. Okay, so now you're operating in the image space. In the sense, your RL algorithm only get images, and it doesn't get the same image when it operates when it goes to the same latent state again. And this magnifies the challenges of the previous environment, because in addition to the sparse reward signal, hardness of exploration, and all that, you're also there's a difference that because you're operating in this image space, your Bellman completeness may not hold. And actually, we can argue that it does not hold formally in the paper.
And all the remaining actions and rewards stay the same. You can take one of 10 actions
Exactly.
and either go to another latent state, draw another class, and so on. So just trying to understand the curve, why is the train set reward? Is it because you're doing that well that the train set reward for HNPG is so much higher than RLPO?
Yeah.
Right.
Okay. There's like one more difference, which is like makes the problem more challenging. So the idea is, so there's a training phase of the RL algorithm, and then there's a test phase of the RL algorithm when you actually evaluate its performance. So you can actually separate the training phase and test phase in the sense that during training, I only give images from the corresponding latent class and the test and the training data set associated with CFAR 100. And during evaluation, I now give the test data images from the test data set from CFAR 100. So there's a generalization gap in the sense you can't really memorize what images corresponding to which class and so on. Like you need to come up with good decoders that can generalize during evaluation.
Yeah, thanks. That answers my question.
Yeah. So you can see like these prior methods actually failed with at Horizon 5. And our reason for why this fails is because the kind of loss they're maximizing is based on Bellman completeness. So they're based on this fitted iteration kind of stuff. And when you do not have Bellman completeness, this loss can blow up. So if you look at the third plot here, the online loss blows up because you're optimizing something in the absence of Bellman completeness. Whereas we have guarantees that hold even when Bellman completeness is not hold. Okay, so let me summarize. Maybe we're like way over the time. We provide a new on-policy algorithm that combines the best of both online and offline data. Our algorithm is computationally efficient when given square loss regression over the function class. It performs well in practice. But the main take-home message from this talk is that hybrid RL is a powerful setting, and it can overcome the challenges of both pure online and pure offline world by providing algorithms that rely on such supervised learning oracles like square loss regression and so on. And in terms of future work, one direction I'm excited about is trying to explore hybrid RL for this agnostic reinforcement learning setting, where we throw away any modeling of value functions, dynamics, and so on, and just ask the question, we are given a policy class, can I return the best policy within this policy class for the underlying MDP? And that's it. Thank you.
Yeah, just a good question. So, how do you choose the offline data while training? So that was a question which I asked in the initial phase, right?
Oh, you mean offline data in these experiments, or oh, you mean the ratio? Ratio. I see. Okay, good.
Yeah, yes, yeah.
Yeah. So in this particular algorithm, the ratio is always 1:1. Uh, so let's go to this one, hybrid actor critic. Sorry, let me find it. Yeah, so in this algorithm, you collect a data set of size D on and a D off. And what you
Mhm.
can show is that, like, okay, we assume 1:1 ratio over here.
Have you experimented with different ratio and found some difference in the algorithm in terms of convergence or the policy it got?
Yeah. So what we have experimented with is where we do not collect fresh data set every time. So you actually reuse offline data set. And that
Okay, and
also works well.
yeah, and which setting did you found to be the best, like in terms of when you are not taking the refresh data or when you are taking a new data every time?
To be honest, did not explore. Uh, I don't know. Like this is a no idea. Like what's the right ratio for
Okay.
this?
Okay, no problem.
But
Thanks.
typically, you can assume that the offline data set, it really depends on like what environment you're solving in. Like for example, for combination lock, getting an online sample is very easy. Like you don't need to deploy a robot or whatever,
Yeah.
and we can like have arbitrary ratios. But if you are like in a more robotics task, maybe like getting an online interaction is not as easy. So we want to study, probably there we want to study like having
Mhm.
ratio where you don't need as many online interactions.
So I was thinking in the terms of adding bias to the policy when we are putting offline data more compared to the online setting. So that was a viewpoint which I was thinking of in these terms. So did you have thought about in similar terms or have any views on that?
So what you can argue, I can show you the kind of guarantee you get for this algorithm. So in some sense, for this square loss minimization,
Mhm.
you get a bound on both the first and the second term.
Yeah.
And over here, there's a nasty expression that looks like so there are two cases. If Bellman completeness holds, you get some bound. If Bellman completeness does not hold, you get some other bound.
Mhm.
And you can see we set this threshold of Bellman completeness to be just the right one that makes sure that both of these are balanced and same as 1 by root t.
Okay.
Yeah. But you
And
do
have you
need to be careful in the sense like there is this issue that you don't want to focus too much on one objective instead of other.
yeah, that was what I was pointing to. Yeah, thanks, Ayush. Yeah.
Yeah.
Yeah, so I had maybe one more question on the same slide you were on.
Mm-hmm.
So you somehow do on policy Monte Carlo rollouts from, let's
Oh,
say, SA where you start off.
yeah.
Yeah,
Yeah.
and you are going to get cases where you um, where there's a lot of variance over the rollout estimates, and these are likely to happen when your I know this is a model free setting, but in terms of the analysis, the probability of reaching certain states is low, but they carry large yeah. So when the transition probability of a particular state is quite low, but it carries a large reward, I guess the variance of these Monte Carlo rollouts is heavy, but somehow you are looking to and I guess that contributes to the hardness of the instance, but somehow this is getting subsumed into the coverage ratio, because the denominator in the coverage ratio seems to indicate the uh, the upper bound on the probability ratios.
Yes.
That is that sort of understanding correct?
Yeah, yeah. So this is for the MPG world, right? Like you're saying, when I fully online guarantee, I get this quantity.
Mm-hmm.
This is what you need to pay for.
Can you go back to the definition of NPG?
Yeah.
Maybe that might clarify things.
Yeah. Mm, This one.
Yes. Yeah.
Yeah, exactly. So this is exactly your intuition. Like, yeah, this is what appears in for this change of distributions.
And the reward does not seem to matter because, like, let's say you're upper bounding the rewards or something.
Oh yeah, so all of these value functions are upper bounded by 1 over 1 minus gamma because like you assume the rewards are bounded between
Yeah.
0 and 1, and this is a discounted setting. So at max it can be 1 over 1 minus gamma.
Oh yeah. I lost that. Yeah. So then this exactly accounts for the sort of variance over the. It's a nice way of looking at it. Yeah. And I guess this is quite common in many of the RL online learning. Sorry,
Right.
in the online learning literature. So
Oh,
this is
you mean
also
like
another way of
you mean bounded rewards for bounded variance or this distribution handling?
this particular CNPG that you speak about.
Yeah,
Is
yeah.
that very common? I've not seen it that often.
Oh, so
And
this is
it's
very common in the theoretical analysis of MPG style algorithms.
yeah, it's very nice. I mean, yeah, I think it's one way to put this variance over the Monte Carlo rule.
Yeah. So like at a high level, if you look at the algorithm, it is very greedy like algorithm,
Mm-hmm.
right? So you do need to say that all the kind of interesting starting points are captured so that I can act greedy on the top of it.
Mm.
That's what it is saying, right?
Repeat that, please.
Yeah. So if you look at this algorithm, this is more like a greedy style algorithm, right?
Mm-hmm.
There's no
Yeah,
nasty exploitation going on.
kind of greedy. Yeah, true.
Right. So all of this thing is deferred to the initialization that, okay, like I can initialize from states that are good enough to capture all interesting behavior.
It's greedy because you want to increase the probability of actions that
That
have higher
have
rewards.
high
Yes,
values. Yeah.
yes. And,
Like
and just to clarify,
there's some noise because like, okay, you are maintaining a distribution over here and so on and so forth. But the feeling is more greedy. You're not doing like exploration out of the way.
it probably it makes sense because at the end, like the way I understood your algorithm is a cumulative reward algorithm.
Yeah.
I mean, it is a cumulative reward algorithm, but you're not sort of the other guarantees that often work in cumulative reward settings account for some variance over estimates, uh, but you don't seem to account for it and yet are able to provide the guarantees required.
Oh yeah.
Um,
That's like a
I'm guessing
technical
it's
thing.
because yeah, it's a technical thing because on the other side you have these pessimism in the face of uncertainty, which says that for the offline, sorry, for the offline RL setting you need to be pessimistic, and in the pure online setting you need to be optimistic. So I guess like not doing anything with the variance sort of makes sense.
Right, exactly. And if you look at this guarantee, it's kind of like saying that I will defer the exploration to either the initialization, which NPG, this term covers CNPG.
Mhm.
Like, okay, the CNPG also covers in some sense like mildness of the MDP in the sense like it's not too hard to explore. But okay, so or I'll defer it to offline data being good.
Mm. Yeah. And interestingly, this guarantee brings there's no term outside the square root, so that's also quite nice. An improvement over, I guess, your own previous work. Uh, I guess the C term was
Oh yeah, so
outside.
there's no dependence on like further structural conditions like rank and so on.
Yeah.
But there is some like hidden log F factor because the number, so there's a hidden log F factor in total sample complexity because you draw like a lot of samples per iteration. So yeah,
Right. For
and
the
like
Monte Carlo.
yeah, there's log 1 by delta and so on. So these things are still there, but there's no rank, like there's no structural assumption that are required except for just these bounded
But
concentrability.
those are also standard, right? Like I guess it's a very fair assumption. Like that's not bad at all.
Yeah, but like I think it's more about the style because the structural assumptions are more rigid in the sense, and I feel like the structural assumptions are more theoretically motivated in terms of like the right properties you need to balance exploration and exploitation. But this is more like a problem dependent quantity in the sense your algorithm can be uh, like you can like try to change your initial distribution and decrease or increase the C of NPG. It's more about the
So
flavor of like what kind of dependency you
sorry,
want to have on.
it's not up to the algorithm to increase or decrease CNPG, right? Or what did you say last?
Oh, I was saying if you want like if you think your algorithm is failing because the CNPG is not nice, you can try to increase your initial distribution so that you start from more diverse scenarios so that you cover all the interesting things and that will decrease CNPG. Or you can try to
Interesting.
collect like better offline data that will help to decrease distribution shift and so on.
Can you perhaps also decrease the size of f? Is that
It's the size of what?
the function class f?
That's something
Does that
I
make
think
sense?
harder to decrease, because typically you do things like, okay, I'll take a 2-layer neural network or 3-layer neural network, and
Mm.
either you go from the 2-layer network to 1-layer network, but you can't do like this kind of pruning that I will like.
Oh, right. I was actually thinking about like decreasing the rank of the linear, sorry, decreasing the degree of the polynomial class. But yeah, maybe the function class is going to be something nonlinear like a neural network or something. Yeah.
Right. And also this degree, for example, in bilinear rank, it's a property of both the underlying dynamics and the function class. So this D is a property of both the dynamics and the function class.
Mhm.
Anyways, yeah, so there are a uh, lot of different settings that people
Yeah.
consider.
So yeah. So great talk, Ayush, as always. Thanks for teaching us whirlwind tour of offline and online RL. I'd like to thank the speaker and just invite him for further talks at IISc again whenever time permits. So
Definitely.
thanks, Ayush. I'll stop the recording here.
Great. Thanks.